Hello, and welcome to the 15th clinic on linear algebra. In this clinic, we're going to be looking at bases and dimension for vector spaces, right? Okay, so we're asked if this set of vectors form a basis for R4, and if not, we want to find the dimension of the subspace that they do span. Okay, so recall that to be a basis, right, the set of vectors has to be both linearly independent and a spanning set. Well, let's first check if it's linearly independent. So to do that, we need to set up the coefficient matrix for the system, the homogeneous system of linear equations, right? And it's linearly independent if and only if that system has only the trivial solution. Well, to set up the matrix, just set each vector as a column of the coefficient matrix, right? So I have 1, 1, 1, 1, 1, 2, 3, 2, 2, 5, 6, 4, and then 2, 6, 8, 5. There's no need to worry about augmenting it with zeros, right? So we RREF this. And what we would like to do is get the coefficient matrix. If we get the coefficient matrix, I'm sorry, not the coefficient, the identity matrix. If we get the identity matrix, then it has only trivial solution and thus is linearly independent. Okay, so we get this. Off to a good start, but then we get this. So what this means is that it is not linearly independent. Huh. So the first three vectors, what this is telling us, is linearly independent. Now, since these four vectors span a subspace, right, then if we eliminate the last vector, those three vectors are still going to span the subspace, right? Hence, right, so let's write this out. So this shows that S is not linearly independent. And hence does not form a basis of R4, right? However, let's call this S prime. Let's go on a new line. These three, right? So this set is linearly independent. And hence forms a basis for the span of S. And this implies then that the dimension for the span of S is equal to 3. And so we now want to find a basis of R4 that contains these two vectors. So what we want to do here, right, is set up a matrix where those two vectors are the first two columns, and now choose any basis of R4. Well, standard bases will work. So 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Now RREF this. So the columns with leading ones are linearly independent. Well, the first four columns have leading ones. So let's call this our basis. The first column of the original matrix. The second column of the original matrix. Then the third. And finally, the fourth. Right, so there is a basis for R4. Right, that contains 1, 1, 1, 1, and 2, 2, 3, 4. Right, so next what we want to do is find the dimension of the subspace W, which is the set ABC, such that A plus B plus C has to equal 0 of R3. Okay. Well, since W is a subspace of R3, this means that the most the dimension of W can be is 3. So the dimension has to be less than or equal to 3. Let's consider the set S. 1, negative 1, 0. That's clearly in W. Then 0, 1, negative 1. And finally, negative 1, 0, 1. Okay, so this is just one set we can look at, right? Clearly, this spans W, right, just by the way that we chose it. So what I'm actually going to do is then verify that this spans, but this is why I chose it the way I did. So to check for span, what we want to do is set up the system of linear equations, right? C1 V1 plus C2 V2 plus C3 V3 is equal to some arbitrary vector in W. ABC. Now, of course, we have a condition that A plus B plus C has to be 0. Right, so what we're going to have to do is do this by hand. Okay. So first step, right, is to do row 1 plus row 2. Right, then the second step would be to do row 2 plus row 3. Right, so from this matrix, what we see is that this system of equations has a solution whenever A plus B plus C is equal to 0, right? But that's a given because it's in W. So this means that S spans W. Now we check for linear independence. Let's make that look more like a linear. There we go. We RREF this. Right? We already saw that from above. This is what we get. So what we do is we eliminate one vector. Right? We only need to eliminate one vector, so let's eliminate the last one, and we say S prime is this here. So therefore, S prime forms a basis for W, which means the dimension of W is 2. What we say now is W is a subspace of R4 that is spanned by these 3 vectors. We first want to find a basis for W and then find its dimension. Right, and then we'll extend the basis found in A to a basis of R4. Well, since W is being spanned by these three vectors, right? Let's just take those three vectors, see if they're linearly independent. If they are, then we have our basis. So RREF this. And we see we're going to need to eliminate the third vector. So this set here forms a basis for W. Right? Of course, that means that the dimension of W is equal to 2. Now we want to extend this to be a basis of R4. Right? Well, this is done the same way as we had done previously, right? All right, so we take those two vectors and now let's add in the standard basis. It doesn't have to be the standard basis, right? Could be any other basis of R4, but the standard basis is the easiest. RREF this. Honestly, it doesn't matter what we get over here. Because we can see that the first 4 columns have leading ones. And so we just take the first 4 columns of the original matrix. And there's our basis for R4. All right, so W is spanned by these 5. W spanned by these 5 vectors. We want to find a basis for W. Right, now keep in mind that W is a subspace of R5, right? So again, it's going to have at most dimension 5. Well, proceed in much the same way. Set up the matrix of these 5. We want to see if it's linearly independent or not. If it is, then we're done. We have a basis. If not, we'll have to eliminate some of these. So let's see what we get when we RREF it. Okay, there it is. Our base is going to be the first vector. the third vector, and the fifth vector, right? Because those are the columns that have leading ones in the RREF. All right, so let W be the subspace of M22 that contains symmetric matrices. We want to show that the dimension is 3. So remember, to show the dimension is 3, we need to find or show that its basis contains 3 vectors. Right, so let's consider the set S. 1, 0, 0, 0. That's symmetric. 0, 1, 1, 0. That's symmetric. Right, and then 0, 0, 0, 1. That's symmetric. So check for span. Right, so we want to show that there exists C1, C2, and C3 such that right, A, B, B, C, right? So that's the form of a symmetric 2 by 2 equals C1 times our first vector plus C2 times our second plus C3 times our first. Well, notice that this equation implies that C1 has to be A, C2 has to be B, C3 has to be B, and C4 has to be C. We found a solution. So this does span W. Want to check that it's linearly independent, right? So to do that, remember, we want to show right, that the zero matrix or the homogeneous system has only trivial solution. Well, from above, C1 equals C2 equals C3 equals C4. I'm sorry, not C4. And equals C3 has to equal 0, right? Because we said that C1 has to be A, and A is 0. Both C2 and C3 have to be B, right? And B is 0. And then C3 had to be C, which is 0. So S is linearly independent. Thus, S forms a basis for W. which implies that the dimension of W is 3. And that concludes today's clinic. Next clinic, we'll be looking at row spaces and column spaces, right? We'll also be looking at rank and nullity. We'll also be looking at the null space. Right, so thank you all for attending. Thank you for watching. I will see you all in the next clinic.